So far, you have seen how nodes are added to the scene, some of their properties, and you have been also introduced to some of the node types such as sprites and labels. Everything you've done so far though has been as static as a photo on the wall. A game, however, needs movement. It needs events that keep the game rolling. In SpriteKit, this is generally achieved in 3 different ways. Number 1. The SK action. Each node can have actions added to them. An action may scale the sprite larger or smaller, it may move the sprite, it may fade or even colorize the sprite, plus many more ways to modify your sprite. SK actions are a powerful and easy way to make changes to your sprite. These changes can even be modified further with different durations between what the sprite is now and its desired result. A single SK action may not be enough to get the desired result. Sometimes you'll want multiple actions to occur in succession or even at the same time. For example, you may want to fade out a label while scaling it down in size. Then after both these actions are complete, you may want it to remove the label entirely so it is no longer taking up memory. You can do that too. The functionality I just described can be accomplished with groups and sequences. These are both arrays of SK actions that look very similar. However, in a group, all actions start at the exact same time, while in a sequence, each action is run one after the other until all actions are complete. Groups and sequences are also SK actions. So groups and sequences can be contained in other groups and sequences. It's also possible to repeat actions a set number of times, or even forever until the SK action is removed from the node. Number 2. Sometimes you'll need more precise ways to change sprites. For example, if you're making a platformer, the character might receive instructions very regularly about where to move, and this might be confusing to accomplish with actions. This is where the game loop is very handy. The game loop is a function which runs repetitively as many times as your device can iterate it. If the term function is new to you, think of it as a to-do list or a set of instructions that the machine has to do whenever you tell it to do the list. So in the case of the game loop, the machine is telling itself to do the to-do lists over and over again as many times as it can per second. To look at this in example, if you put in your function that you would like a man to move left 1 pixel, as this function repeats over and over again, the game runs and the man continuously moves to the left. This is a very basic example, but there is potential to add a lot of complexity to this function, so that it is constantly checking the state of the man and any other sprites to see if they are currently moving, if they are still on the screen, if they are touching another object, etc., and handle these interactions accordingly. One thing to note about the game loop is it always runs as fast as the software can allow it. It does not keep a consistent pace. That's not good in a game situation. You want your sprites to move smoothly and to keep perfect time sync. This can be achieved using some simple math on the time interval to get what is called delta time. This is the elapsed time between the last game loop function and the current one. It can then be used to adjust movement speed and be consistent with time. And number 3. So far we have looked at using SK actions and the game loop, but there is one other important way objects can be affected, and this is with the physics engine. The physics engine is quite powerful, and the code is fairly easy to learn. That doesn't mean it has no cons, but it means you can get up and running quickly. So you have a static scene. Now imagine you want to add gravity to it. You can do that. Nothing moves though, because you haven't told each object how it is meant to react to gravity. So then you tell your human that it is affected by gravity, and the human falls off the screen to his doom. It's not always useful to have a forever falling doomed man, so you can add what is known as collisions. When the person collides with the floor, it does not pass through the floor. For this to work, you need to tell both the human and the floor that they are on the same collision bit mask. Sometimes you don't always want objects to collide, but you still want to know when they've made contact with each other. For example, if you make contact with a coin, you probably want to collect that coin. You can do this by setting contact bit masks, which work in a very similar way to collision bit masks. Let's back up briefly to talk about how the physics engine knows how to handle each object. The scene itself has a physics world property, where you can tell the physics engine that this scene can track contacts and collisions. Each node within the scene has a physics body property. In here is where you set if the node is affected by gravity, if it collides with other nodes, and if it contacts with other nodes. You can also set one other very important thing, and that is the physics boundary. For a human, it might just be a rectangular boundary of the image. If he was, however, a ghost, and you wanted him to levitate above the ground, you could extend the size of the rectangle down, and he would then collide with the floor underneath his image. If your sprite was a ball, then a rectangle probably wouldn't be the best fit, and it would look pretty ridiculous when you use it with other objects. So you can use a circle instead of a rectangle. There are other options to draw custom physics boundaries and automatically draw it based on the image, but keep in mind that these options have a much higher performance overhead, as the physics engine has to make a lot more calculations per frame. Moving nodes with the physics engine is done by placing impulses and force on nodes. By telling the physics engine that you would like these objects to move in this way, it can do all the complex math for you. So those are the three main ways to perform actions on nodes. Don't feel like you have to pick and choose which you will use. They all have different pros and cons under different circumstances, and some of the best games I've played are the ones that manage to use all three methods really well in the one game. Now it's time for the practical example of these three methods.